We just did exponents, but the exponents were all numbers. An exponential function specifically has a variable in the exponent position. So you'll notice that I have like 4 to the x, 1/3 to the x, 7 to the negative x. Whereas what you just did for bell work, you had the variables to a power, not something to a variable power. So for it to be an exponential function, your exponent must be a variable or a function of a variable. These are not exponential functions. They have exponents, but this -3 is the exponent. That is a number. It's not a variable. Pi is a number. Why would this not be an exponential function, you think? The reason this isn't is because this is just 1. That is a constant. 1 to any power is 1. You can take it to any power you want. It is 1. 1 times itself any number of times is 1. So that's why that one in particular is listed that way. You are not going to have to graph these, but if you'll recall, exponential functions, we've done, I think, square roots. So you've seen like what a power does to a function. Exponential functions shoot up quickly. Linear functions are this steady increasing line, right? So when you think about linear functions, they grow at the same rate. So as you walk across, it's increasing at the same exact rate, hence your slope of the line. But exponential functions will shoot up. And so we're going to do some like investment type of equations. And so investments climb up faster than a linear equation would because you're doing this exponentially, compounding it exponentially. And so that's what your graph is going to look like because it is rapidly increasing, or if it's decaying, it's rapidly decaying versus a steady, rise over run type increase or decrease. And then here's some properties. You don't have to know the domain and range, but you just have to know what it means. Exponential functions have no domain limitations. You do have a range because you're not going to drop it into a negative if your base is already positive. Same thing with decay. All right, let's look at some compound interest. These are investments. So principal, that's how much you invest. R, that is your rate in decimal form. 5% would be 0.05. N is the number of times a year that you compound your interest. All right, so we have several variables here. Principal. And then T is the number of years. T is the number of years that you are compounding it. All right, so number of times you compound a year. What they mean by that is they take your principal, they calculate your interest, and then they put that interest on your principal. And then they take that new amount, your principal plus the interest you've earned, and now you're earning money on that total amount, okay? This can also work against you, i.e. credit cards, all right? So credit cards compound, all right? And so what they'll do is they'll take your balance, they'll apply their interest charge. So your balance plus your interest charge will become your new balance. And so then your interest card total will be climbing as well. And so very often the interest charge is more than the minimum payment. And so you're never actually paying your credit card off. All right. But this is the formula. So this is the formula you will use for compound interest. It says Christy invests $300 in an account with a 6% interest rate, making no other deposits or withdrawals. What will her account be after 20 years if it is compounded? And they've given us 3 scenarios. All right, so let's look at this first one. I'm going to say, well, her account balance will be her principal times 1 plus, what was her interest rate? 6%. Number of times, if it is semi-annually, how often per year are they compounding? Right, so 2 times a year. So I'm going to raise that to that same number n times the number of years. This is how you would do it. You can put this in your calculator exactly like this. So you're going to put in your calculator 300, and then you're going to do times. You're going to open parentheses, 1 plus, and you should be able to do 0.06 divided by 2 if you have like a regular larger calculator there. If not, you're going to do it piece by piece. Your little caret top, and you can actually do I'm going to show you here in case you have one that's not easy to calculate. You do need to do open parentheses here. 2 times 20. If you do not, it'll raise it to that power and then it'll take the answer times 20. So in your calculator, you want to do it just like this. Monthly. What's the only thing that's going to change if I say monthly instead of semi-annually? On monthly, I'm going to do the same exact equation, but my n is going to change to what number you think? If 12. Yeah, 12. Daily, same equation, but 365. Daily is how many times a year? Yes, daily would be 365. Right there. We're going to talk about it a little bit more. You will have a new formula for continuous compounding. That E is the natural number E. It's Euler's number. In your calculator, you will have E to the N or E to the X power somewhere. If you see the LN on your calculator, it is usually above the LN. So you might have to use a shift or a second key above your LN. All right? So this is your principal, and then your E to the rate times time. This one is, for some reason, easy to memorize because it looks like a word, right? PERT. Continuously compounding is PE to the RT. So suppose she finds an account that will allow her to invest $300 at 6% rate continuously compounded. No other deposits. What will her balance be? So you literally in your calculator will put 300, not with those big highlighter notes. There we go. 300 times, and you will put in your E. Like I said, in your calculator, you'll usually have to do a shift or a second. LN, that is your E button. Raised to the, and you will have to do parentheses here, 0.06 times 20. So it's going to be 300 E to the 0.06 times 20. And this is what it looks like in your calculator.
Last time I got like 36,000.
So while principal and interest is the most common form of exponential growth and decay, and the second most common really is in science. Okay, so you'll see this in science. It looks exactly the same. If your growth rate is a number of times per however often they're measuring, this should look really much like your other one, okay? But they give you the time, so they'll say every hour or every day or whatever. And so your times that it happens is just once every day or once every hour. And then your T represents how many days or hours or whatever that you actually compounded, all right? This one should look familiar as well. While it's not PE to the RT, it's your initial condition E to the RT, which is all what the P stood for. So you don't really have to memorize a second formula for growth and decay. You just have to pay attention to what they're talking about as far as it goes. Mexico has a population of approximately 110 million. If the population continues to grow at the described rate, predict the population of Mexico in 10 and in 20 years. So for this one, we are simply going to plug it in. Initial amount. Well, that's the amount that they gave us right here, 110 million. So we're going to say 110 million is my initial amount. And then my rate. Well, they gave me the rate here, 1.42%. I need that in decimal form. So don't forget to move it over 2 places. 0.142. And then amount of time. Well, they said 10 years. So I would put 10. For 20, I'd put a 20 in, okay? Continuously. Well, for continuous, I'm going to use this one, 110 million. E to the R, that's going to be the same thing I put over here, 0.142 times 10 years. So learn to recognize growth and decay problems, whether it is principal and interest or whether it is population growth. Another really fun one they like to do is bacterial growth. Very often they'll use radioactive decay. So for decay, you're going to have to use a negative percentage for your percentage because it is shrinking, not growing, okay? And so pay attention to the verbiage that they use in these word problems. Whether it says it's continuously changing, if it's growing, or if it's decaying. You're going to pay attention to those for like positives and negatives. All right? Questions on that? All right, so try this last example, and then we're going to do the next section. Pay attention to what it says.